Yeah. We finally got the group form in, but still haven't. We don't know who's going to be the leader. I think no one wants to be the leader.
That's true even in the adult.
I mean, I don't mind reminding people, but it's just telling them what to do. I don't really like that. It's like, look, hey, look, wait, deadline is coming up. Just got to do what you got to do.
Yeah, it's uncomfortable for everybody.
I
No one wants to be the bad guy.
I did it like 5 times in my college life. It's like I'm had enough. This morning was pretty bad. There was a lot of accident coming up here.
Oh, really?
I luckily avoided most of them, but,
Uh-huh.
but the people coming 8:30 just hadn't hit the old
Oh,
accident
goodness.
traffic.
Yeah, it took me longer than usual. I mean, usually it takes me almost an hour, but not quite an hour to get here. But today it took like a little bit over an hour. So
You live in Cyprus. I live in Seal Beach. We're like almost 15 minutes each other.
oh no, my parents live in Cyprus, but I live in Ontario.
Ontario. Okay, I thought you said Cyprus.
I'm going to visit my parents after today's episode. Wish I could live in Cyprus, but CSU doesn't pay me enough money to live in Cyprus.
Because it only takes me 35 minutes to get up here, going 80 miles per hour. Or 133 kilometers.
Something like that.
I had to memorize that when I went to go off country roads, out of country.
All right, 410 people. So we have an ANSYS activity today. And so if you want to start up Workbench, I'm going to do that right now. Then we can kind of hit the ground running once it begins.
I was completely good with everything, but I was all stationary. When nothing was moving, I was like, oh, I got this. Pressure, started moving on. It's like,
Yeah.
So,
Yeah.
he was like doing it.
Not working. Start thinking about the midterm project or something like that.
We'll talk about it next week.
Oh, okay.
Mhm.
Oh, I thought about that.
You'll have over a month to do it, but yeah, I'll introduce it next week. Yeah, after activity 3 is a good time to. Because I think what I've seen generally is that after activity 3, then students kind of start feeling pretty comfortable with ANSYS, and so that's a good time to go.
Certain part, I think it's like 400 classes, and then there's 318. Just don't really. Yeah. Just trying to. I just need one more after this semester. Oh, yeah, I'm like Chicago, sleeping. Oh, wait, I'm taking. So that's deal. Someone was about that class.
Trying to see the new graphics card coming in.
I did. Yeah.
How you think about that?
I've never been a super high-end person. All my friends really are, but I'm still using the same laptop that I bought like 6 years ago.
No need to upgrade as long as it's working.
Yeah, it plays all the games that I want to play, so it's good for me. All right, so it's not 5:30 yet, but today is an ANSYS day, and so if you guys want to start up ANSYS Workbench, if you want to go onto our Canvas site and download the CAD file and the instructions, then you can do that. But we'll get started at 5:30 today.
I'm thinking of flagpole, not signpost. That's why I'm getting confused. I never seen a flagpole looks like that.
It's a pretty big flagpole. Oh, is it? Okay. I see. All right, it's 5:30. Let's go get started. All right, good evening, everyone. How's everyone doing today?
Surviving.
Surviving, that's good. That's the best you can do. As long as you're surviving day to day, that's good, right? Okay, so today is an ANSYS day, and so we're going to be working with ANSYS. So it's our third activity, and so if you haven't already, go ahead and start up Workbench because I know that takes a little bit of while to do. And if you go on to Canvas, you'll see that this morning I created the activity or the assignment for activity 3, and so you can download the PDF. And then just for today, we're going to be working with the first CAD file here. So the solid signpost geometry base.agdb. Okay, so go ahead and download both files, start up Workbench, and then we will go from there. So while everyone's doing that, let me update you guys on some things. And so I think last time we were here for ANSYS, I think I told you that I would look into seeing if we can update the versions for ANSYS here in the lab to 2022. So literally the day after I said that, I think we got an email from the dean's office saying that our IT person no longer works here anymore. And so literally the day after I said I would talk to IT, see if we can do it, and then the person that could do it no longer works here. And so
that person just start too.
yes. Wow. So I mean I don't know what happened, but he's not here anymore, and so. Let's just kind of assume for the foreseeable future that this is just going to be how it is. And so you're going to have 2021 here in the lab, and then on your laptops, if you're working at home, it's going to be 2022. And so what I saw a lot last time was I know a lot of you guys brought your laptops here to work on the activity on your laptops so that you don't have to transfer files. And so if you have that option, that's great. But if not, then I think try to make sure you finish as much of the activity here as possible. And then, make some time, either, come in tomorrow or, sometime after that to work on it in the lab. Okay. So with that in mind, I am giving you a bit more time than usual. And so normally I give you guys a week to finish the activities, but I'm going to give you, until the Monday after. And so this will be due not next Monday, but the Monday after that. So Monday, October 3rd. Okay. So just to give you guys a couple more days if you need to come into the lab to work on the activity. Okay. All right, and so here's our third activity. And so we are going to be working on simulating a signpost. Okay. And so kind of your visual for this is, if you're driving on the freeway, you see those signposts on the freeway that tell you, when your exit is. And so that's basically what we're designing here. Okay. And so there's quite a few loads on this one. And so, we have a lot more boundary conditions than normal. And so, we'll kind of walk our way through that. Okay. And what else is new about this one is that we're going to be working with an assembly. Okay. And so technically activity 2 was an assembly, but we only worked one part of the assembly. This time we're going to be working with multiple parts, and we're going to see, what that entails in ANSYS and kind of what extra work that you need to do. Okay. And so just like the second activity, I'll go ahead and walk you guys through kind of the beginning parts. a lot of the new features that we haven't gone over in ANSYS yet. And then, but for the rest of the activity, I'll kind of let you guys do, I'll let you guys kind of work on your own. And I'll just kind of walk around and help people as I can. Okay. Okay, and so I think that's all the announcements. So are there any questions before we get started with the activity today? Okay, all right, and so let's go ahead and get started. And so, oh, I haven't downloaded this yet. So let me go ahead and download this. Okay, and so first thing we're going to do is we're going to open up Workbench and we're going to start a static structural analysis. And so just like we've done before, we're going to take static structural and drag it over into the project schematic. Let's go ahead and import our geometry. And so you're going to right click geometry, go import geometry and browse. Okay. And then navigate to the area where you downloaded the CAD file. Okay. And so the good thing about this project here is that this geometry was actually created within Design Modeler or within ANSYS. And so there should be no compatibility issues and it should load just fine. Fingers crossed. And so I'm not going to check the geometry. Okay. What I am going to do though is I'm going to add a new material property. Okay. And so just like we did in activity 2, we're going to double click on engineering data here. Okay. And so double clicking on engineering data will open up this new tab here. And then exactly like we did last time, we're going to add a new material for aluminum. 6061. Okay. And we're going to add the following material properties. Okay, and so just like we did last time, we're going to go to linear elasticity. We're going to double click on isotropic elasticity, okay? Because remember, we're assuming that this aluminum is an isotropic material. Okay? And so that'll allow us to specify the Young's modulus and the Poisson's ratio, just like last time. Okay? Make sure to change your units here. And so remember, when we're defining our Young's modulus, we're doing it in terms of PSI. Okay. And so if you do pascals or if you do some other units, you're going to get weird results. And so make sure that you're on PSI and your Young's modulus here is going to be 1E7 and your Poisson's ratio is going to be 0.33. Okay. Okay. All right. There is one more thing that we're going to do here. And I need to find it again. Yes, the density. Thank you. And so we need to add the density here, okay? Because we're gonna do a new type of loading in this activity where it's called standard Earth gravity. And so what that means is that we're gonna apply the weight of the object itself as another load. Okay. But in order to do that, you need to specify the density. Okay. And so density is under this heading right here called physical properties. And so make sure you have aluminum 6061 highlighted. Double click on density. Okay. And then we're going to specify the density here. And so the density that we're going to put in is going to be in the units of pound per inch cubed. Okay. So make sure you're on that units there. And the density is going to be 0.0975 pounds per inch cubed. Okay. Yeah.
Once it's centered, can we change the units back to?
Oh yeah. So so this is just for specifying the material property. So once you're in ANSYS, you can change the units to whatever you want. Yeah, and actually, if you notice that if you put the density in here, and if you change the units, it'll automatically convert it for you. So if you change the pound per feet cubed, it's a 168.48 pound per feet cubed. Okay? And then if you switch it to kilograms per meter cubed, it's or kilograms per millimeter cubed, it's 2.6988 e to the minus 6. Okay? But the one that I inputted at is pound per inch. Okay? So make sure that you're setting the right units, and if you're curious about the conversion, you can switch those. All right. So that was a little bit fast. And so was everyone able to specify all 3 material properties? So Young's modulus, Poisson's ratio, density. Everything's okay. Okay. All right. And so if you specified those material properties, let's go ahead and close this out. And then we're going to open up model. So go ahead and double click model. And so that's going to open up ANSYS mechanical. Cancel. Part always takes a couple minutes. Okay. All right. And so your geometry will look a little bit different than the one in the PDF, and that's because I added this little base in here to kind of help kind of stabilize some of the results. Otherwise, it gets a little bit funky. Okay. And so if you open up ANSYS Mechanical and you loaded your geometry, it should look like this. Okay. All right. And so, for the first time, this semester, we're actually going to be working with all parts of this assembly. Okay. And so this assembly here is consisted of actually 3 different parts. And so we have the post. Okay. And so the post is just the cylindrical post. We have the sign part. And so the sign part is just the rectangular part above the sign. And then what you'll see also is that we have this kind of like a little bit of a strip here. Okay. And so it's almost like a piece of tape that's kind of running up and down the length of the signpost. Okay. So we'll come back to that in a second. But the first thing that we're going to do here is we're going to make sure that we specify the correct material properties for each of the parts. Okay. Okay. All right. So first thing we're going to do is we are going to specify the material properties for the sign. Okay. And so if you read the PDF, then you'll see that the sign here is made of aluminum, whereas the post, because the post is going to be doing most of the supporting, this one's going to be made of structural steel. Okay. And so let's go ahead and click on the sign, and then under material assignment, and so in the bottom left, you'll see this area right here. And so with the sign highlighted, you're going to change the material assignment to aluminum 6061. Okay. And so once you do that, then the sign is going to have the, all the material properties that we just inputted. So it's going to have the right density. It's going to have the right, Young's modulus, as well as the Poisson's ratio. Okay. Okay. So now that we've changed the material properties of the sign, that's good to go. The post is supposed to be made out of structural steel, and so we can leave that alone. Okay. And so the last thing that we're going to change here is this strip. Okay. And so the purpose of the strip, I like to call these things phantom surfaces. And so they're not a real surface in this model, and so we're not actually modeling a piece of duct tape on this signpost. Well, I wouldn't be surprised if there is some duct tape holding those things together. Okay. What this is going to allow us to do is that it's going to allow us to apply a load. Okay. And so if you go back to the problem PDF for a second, let me go back to that PDF. Oops. If you go back to the PDF, you'll see that there is a force here that is being applied on the vertical surface of the signpost. Okay? And so we call that force WX2. So that WX2 is going to represent a wind force, but it needs to be applied basically just only on that left side of the signpost. Okay. And so if we didn't have this strip right here, it would actually be very difficult to assign that force, because if you try to click on, just anything, you either highlight the entire, the entire surface of the post or not. Okay. And so if we just click on, maybe just this side of the sign right here. Okay. And so that takes care of that, but then, we can't apply the force down here. Okay. And so what we did here with this part was we created a very thin surface here that kind of stretches from the very top and bottom. Okay. And so this strip here, it's not going to add any structural strength, but its only purpose is to basically allow us to apply a force. And so if you kind of click on that strip, there you go. You'll see that it highlights green and it goes all the way up and down. Okay. So this is a very common technique in ANSYS, because a lot of times when you apply a load, there's no convenient surface for you to apply it on in your default geometry. And so sometimes you kind of have to make up a surface or kind of project a surface onto another. And so we'll go over how to do this later on in the semester because it is quite useful, especially for your final projects. But for now, we're just going to use it. Okay. And so the only thing we have to do, even though it's a made up surface here, it still has to technically be part of the model. And so we have to specify a thickness. Okay. And so if you notice, if you click on this WX2 application surface, there is an entry here for the thickness of that surface, right? And so I went ahead and I changed my units to inches. Okay. And so we're going to specify just a very negligible thickness here. And so this is going to be 0.001 inches. Okay. Right. And so it's negligibly small. And so it's like basically, 1/1000th of an inch. Right. And so, and remember, the point is not to add any structural strength. It's just to give us somewhere that we can apply a force to. Okay. Any questions on that? I know that part of this activity is a little bit weird. Yeah. Wait a second.
I'm trying to get the signpost file off of Canvas. It's just, but every time I open both of them, I can data shares.
Oh. I'll come back in a second. It could be that I overwrote the file, but I just downloaded just now, and so maybe try to just refresh your browser and then and I'll come back there. Is anyone else having that issue? Everyone else got the signpost? Okay. Okay. Yeah, I'll come back there. I'll come back there in a bit. Okay. All right. Any other questions on this part right here? Yeah. Yeah, you can keep it as steel. And so it's going to be so thin that it doesn't really matter what material we put it on. So we can just leave it as the default. Yeah, good question. Okay. And so the next thing that we're going to talk about here are connections. Okay. And so this is something that's unique to assemblies. And so when you have multiple parts kind of interacting with each other in a finite element simulation, you have to define how they're going to interact. Okay. And so that might seem like a strange thing because for this particular case, we even though it's an assembly of parts, we kind of want it to behave as if it's one part. And so we're basically going to assume that this sign is basically bolted and welded onto this post. Okay. And so there should be no separation, no sliding in between the two parts. Okay? But there might be some situations where you do want some some kind of sliding or maybe some kind of friction. Okay. And so the way that you can define that is through this through this tool here. Okay. And so if you click on contacts or connections and contacts and you kind of expand this tree, you'll see that it's created 3 contact regions. Okay. And those contact regions are basically defining the interaction between 2 different parts in your model. Okay. And so for instance, I'm going to click on contact region 2 here. And if you look in the bottom left corner, you'll see the 2 parts of your assembly that are interacting through this contact. Okay. And so for this particular contact here, this is defining the interaction between the sign and the post. Okay. And so that's why both parts are listed here. And then the other contact regions are between the strip and the other parts. And so this is the strip and the sign. Contact region 3 is the strip and the post. Okay. All right. And so from here, you can define, how these parts are going to interact. And so basically once the simulation begins, you can say that, it's okay for these parts to slide past each other. Maybe they slide past each other with some friction. Maybe you don't allow them to separate. Okay. But the default setting for this is bonded. Okay. And so if you look at the type here, that defines, how those connections are going to behave. Okay. Bonded is the default. And so what bonded basically says is that, these 2 parts are kind of, welded or super glued or bolted, whatever you want to, however you want to visualize it. And so there should be no separation and no sliding in between these parts. Okay. And so for this particular activity, that's exactly what we want. And so we don't want any separation. We don't want any sliding. But for your final projects, especially if you're going to do a dynamic simulation, maybe you want some contact, or maybe you want some sliding, or maybe you want some friction. Okay. So for here, we're not going to do anything. We're just going to leave it as it is. But I just want to make you aware of that feature. Okay. One thing that we will do here is we will rename these. And so, so far, it hasn't really been an issue in our first 2 activities because, we haven't had that many parts, we haven't had that many loads. But you'll see that, once you start working with more complex assemblies and with lots of loads, it helps a lot to label these quantities, okay? Because when you go back and you check, it's really helpful to read, what this part is defining rather than just contact region 2, which, doesn't tell you when, okay? And so to rename something here, you can highlight on it. And so you can right click and you can hit rename. And so what I like to do for my contact is I like to kind of rename it based on the parts that it's contacting, okay? And so here, I'll call this the post sign connection, okay? And so this tells me right away, what this connection is for, okay? Next one right here, this is between the strip and the sign. So we'll call this strip sign connection. Okay, and then this one right here is between the strip and the post. We'll call this strip post. All right, so you don't have to do this, and so this is mostly optional, but I will tell you that once you start getting into more complex projects, renaming your stuff is really important. Otherwise, you're going to get lost in your own work. So you're going to be applying 7 different loads, and then by the 7th one, you'll be like, did I apply this load already? And then you're not going to know because you didn't rename your stuff. And so it really helps staying organized, and staying organized is important for these kinds of projects. Okay. All right, and so that's it for the strictly new stuff that we haven't seen before. And so the next step, of course, is the meshing. I'll kind of let you guys do that on your own, though. Okay. The only thing I will require in this one is that you mesh the sign and you mesh the post separately. Okay. And so you should apply different meshing settings for the sign and the post. And so what that means is that you should have a method object for the sign. Okay, and so you can choose the element shape and the element order for the sign. Okay. I want you to make a sizing object for the sign, and so you can specify how big you want the elements there. And then you're going to have the same thing for the post as well. Okay. So method for the post, sizing for the post. Okay, I'll let you decide, how you want to size those things, but kind of remember what we talked about in terms of mesh. What types of elements work well for certain geometries, and where do you want to focus the element defining. Okay, and so think about where you expect the stresses and deformations to be the mostly the stresses, and so think of where you expect the stresses to be the highest, and then that's where you want to concentrate most of your elements. Okay, but I'll let you guys kind of decide that on your own. But what I did want to go over together was the loads, because these are a bit different than kind of what we've been used to. Okay, and so first thing we're going to do for the loads and constraints is we're going to fix it. Okay, and so just like we've done before, we're going to add a fixed support. Okay, and for this case, it's fairly obvious where we're going to fix it because this post is going to attach into the ground, and so we should fix it on the bottom surface. Okay, so make sure you apply a fixed support. Okay. All right, next thing we're going to add here is the weights, okay? And so, this is a fairly big object, and so the sign is going to have significant weight, and the post is going to have significant weight as well, and that's going to significantly alter our results, okay? And so, luckily, there's a very easy way to add weight into a simulation. And so we're going to right-click Static Structural A5. We're going to go to Insert. And we're going to go click on the load. Where is it? Right here. And so if you look near the top, of the list, there is a special load called standard Earth gravity. Okay. And so if you read the description of standard Earth gravity, it'll tell you that it inserts a boundary condition that simulates the gravitational effects on a body in the form of an external force. Okay. And so what this is going to do is that it's going to calculate the weight of each part of your model based on the density that you gave it. And the gravity constant. Okay. And then it's going to apply that force throughout the entire model. Okay, and so the nice thing about standard Earth gravity is that you don't have to apply anything. Okay, and so you just have to put it there. Okay, and if you want to verify, this is giving you the acceleration due to gravity. And so you want to verify this in meters per second, you can see it's minus 9.8066.
What if we were to do that and it gives the direction of gravity? Like right there, it's perfect, but what if it auto did it to the left? How would we change that?
Yeah, and so you can change it from here. And so hopefully, and so of course, this means you would have to align the gravity to one of the coordinate axes directions. And so it can't be a diagonal direction, but you can change which direction. So, yeah, good question. Okay, but for now, the minus z direction is kind of what we want, and so we'll leave that as that. Okay. And so in addition to this, so that takes care of the weights of the parts. Okay. And so are there any questions on this so far? Everyone able to add standard Earth gravity and fixed support? Yeah. Yeah, so you might have to change your units. And so if you change the units to SI units like the metric, and it'll be minus 9.8. Okay, so there's two more forces that I want you guys to add. And so both of those are going to be from the wind. Okay. And so one force is going to be directed at the middle of the signpost. Okay. And so we're going to add this as a force load. Right, and so I think the magnitude of this force is going to be, what is it, 8,000 pounds. Okay, so we're going to switch the units here to pound force. Okay. But the application of this force is going to be interesting. And so, we talked about this a bit on Tuesday in terms of how you want to apply the boundary conditions. Normally, you don't want to do this because you don't want to apply force at a point. I'm just doing this for just educational purposes. Okay. And so to find the point, and so if you switch the selection mode, and so if you look on kind of this part of the ANSYS interface, you can change which kind of selection style that you want. Okay, and so in this particular case, we're going to look for a point, and so you're going to click on this left one right here. Okay, or I guess you can do Control P. Okay, and if you kind of mouse over the middle of the signpost, you'll see that there's a dot. Okay, and so you're going to click on that dot. And then you're going to apply the geometry there on that vertex. Okay, and so you should apply that force on that small point, just like that. Okay. All right, and so from here you can apply the force magnitude, and so just like I normally do, I like to apply it in components, and the magnitude of that force is going to be 8,000 newtons going in the positive. 8,000 pounds going in the positive y direction. All right, and so that force is being applied at a point, and so there's not much to that force. It's just you have to find the point, and so make sure you're on point selection mode or vertex selection mode to find that point. Okay. The last force that we're going to apply here is a vertical pressure force. Okay, and so remember, if we go back to the problem statement or the project or the activity specifications, you'll see that there's a force that acts kind of on the side here, right? And this is where the strip is going to come into play. Okay. But what you'll notice here is that the force is varying. And so it varies from 0 all the way up to a maximum value here. Okay. And so this is kind of a good place to show that when you apply loads on ANSYS, it doesn't have to be a constant value. So you can actually have a varying load that varies from one point to another. You just have to enter it as a function. Okay. Okay, so let's come back to ANSYS mechanical, and let's right click on static structural, and the type of load that we're going to apply is a pressure. Okay. Okay, so let's go ahead and click pressure. For the application surface, you're going to select that thin strip, and so kind of make sure you're on kind of space selection mode. Actually, it kind of forces you to, and you're going to try your best. Zoom in if you have to. Let me close these things so you can see better. And you're going to click on the strip. Okay, so make sure you're only clicking on the strip, so nothing else is being highlighted. Okay, And then once you've selected the strip, go ahead and apply it to the geometry there, okay? And now we're going to enter the magnitude of that pressure. Okay? But before we do this, because we're going to be inputting a function, you want to make sure the units are correct. So, before you input the function there, you want to make sure your units are in US customary with inches, okay? And so there's 2 US customaries there. You want to make sure you're on the second one with inches, okay? Otherwise, you're going to get a wrong force. Okay, and so double checking that your units are in inches. Okay. Now we're going to apply the magnitude of the force here. Okay. Okay. And so the function that you're going to specify here is it's going to be a function of z, okay, because the force is going to change in the z direction. And so to input a varying force, okay, so I'm here in the bottom left. To tell ANSYS that you're going to input a function, you're going to put an equal sign. And so just like Excel, when you're inputting a function there, okay, you put an equal sign, and then you're going to put the value of the function. And so for us, it's going to be z for the z coordinate multiplied by 0.1. Okay. And so what this says is that it's going to tell ANSYS to take the z coordinate of wherever you are on the signpost and then apply a pressure force that's 0.1 multiplied by that z coordinate. Okay. Okay. And so that should be good right there. Okay. All right. Yeah, it's a little bit hard to see, but it's 0.1 times z, or z times 0. Okay. Okay. And so last thing I'm going to do here, just like I did with the connections, I'm going to go ahead and rename this. And so this force right here will be the point wind force, okay, because it's the wind force that's at a point. And this pressure force right here, this will be the varying wind pressure. Okay. And so in case you have to go back and kind of modify these things. Okay. And so let me go ahead and highlight this one more time. And so just for people to see what the function is. Okay. All right. And so from there, you guys can take it from here. And so, go back to the meshing, make sure you apply the mesh sizings. And so, play around with that. And then with these boundary conditions, the way that they are, you should be able to start running some simulations. Okay. And so I'm gonna start kind of making my rounds and kind of go around. And so if you need some help, go ahead and raise your hand and I'll come around and talk to you guys. Okay? But the rest of the activity is in your hands now. Yeah, because normal too, but the perpendicular. And so if you want, you can do that. Yeah, for this case, the default here was already. And so for those, you have to kind of go back and look after when we talk about meshing parts. Like say for instance, so you have 2 parts. You have one part that's literally a rectangle, another part that's square. You talk about 2 different elevations. Versus the rectangular ones, which work really well when they can, but they only really work with some water. So for that, you would say that I would take I would pick square or technically for the signs. For the sizing, you talk about how the accuracy goes up as the right side. And so you want to make sure you get on this, you're only interested in so you'll see when you run, you'll see that there's areas you want to make sure that you have Want to concentrate accuracy.
I was gonna do attention fusions for the first.
No, but you're keeping size.
Size, yeah, size is.
Yeah.
If you have, so in that middle example, it's a billion. And so, you try to run that on every element is kind of like, you can think of it as like
Generated.
I think so to run a billion computations. You can try to run balance it, how much accuracy. Cost you.
Yeah.
So for, and I'll say for our.
It is not.
I know they left one course a day,
But in reality.
and they left one guy. And
The
so
difference is like when I see them and stuff is like waiting a day. Getting simulations over the day.
based on time, right? Pretty like wide margins. They really need. You know. Like if they're starting at like 19.
Oh, well, yeah.
I'm pretty sure you do.
Exactly. So it's always a balance. Of course,
This one starts at.
it's like.
Yeah, it's right.
Say like you got, hey, you two.
It's like how do you? That's why you guys know these things. This one doesn't. This one doesn't matter. It's not that. Oh, okay, yeah, and the rest of the.
So it's not in this device, we want to be able to do like a ladder like this. Elements, or we're just gonna do like the triangular ones. Yeah. So that mesh, it tells you the mesh type, and when you use body sizing, that's where you specify how big or small.
Yeah, so the ones.
I don't know.
Yeah. So the. What you, and so when you run this. And remember, you know, you want to make sure that you get. You're tuning. The one result that's always the hardest is. So what you want to see. The result, you see that. So what you're going to want to do is. But then the side, you see the side that's what goes stress. For a stronger side, you have to go off. You have to make it bigger. Yeah. Make the element bigger. So we, so ideally, but we don't have to go. Someone just asked, so your thought process kind of so you want to make sure that we have some accuracy on our. Usually we have usually it's not as powerful. Usually with like professional, but you don't really have time to. One portion That's perfect. That's right. That's perfect. I think that might be a sort of I would just use I'm hoping that it'll fall. You would think so. We should have. Right. Zoom people, any questions? Okay. All right, yeah, if you come up with any questions, just drop it in the chat. So I'm walking around, but I can see when you guys post in the chat. And so yeah, once you run into anything, just let me know. I'll make a couple more rounds and then we'll talk about the later parts of the activity. Number 5.
we're doing our own software.
Oh, yeah, so for 5, you're gonna actually modify the part that you designed. So
I'm just reading it. So I'm gotta go on.
yeah. And so for that one, you can actually modify this part. So if you go back.
Just like put some stuff in.
Oh, yeah, we did that. Yeah. So what you can do from there is that you can adjust like this. So I don't want you guys to read. You can adjust like the size of both.
Yeah, but
Someone said online, if it takes too long, then just change, you have to increase the element size, because then it goes faster.
I think it's just two different scenarios.
Yeah, I'll put 2.3 millimeters, so, yeah. I think it's maybe it's a long too.
I had it at 1.5.
No, that's fine.
Oh, did you have? Oh, yeah, that's.
Yeah, I'm gonna give up too. It's taking too long. Actually, if you think about 1.5,
Yeah, so
that's like 30 millimeters, so that's pretty big.
Looks like you can
That's
We can run it where we're at now.
How many elements do you have, DJ? And so if you check, if you go to your mesh right here and you go to statistics, you should get the number of elements you should get should be somewhere in the ballpark of like 20, 30, 40,000. And so if it's around there, then that's good. Yeah, but I was telling people too that you want to be a little bit strategic about how you allocate your elements, because you know you have a total number of elements that you can have. So I think it's around like 51,000 or something like that. And so that's the maximum total number of elements that you can have. And so you want to be a little bit strategic about how you allocate that. So, you know, for this activity, you know, there's two parts here. So there's the sign and there's the post. Okay? And so you want to really think about, you know, where you want most of your elements to be. Okay, so you're kind of right at the limit. So I think you can push past 51K might be the old limit. It might be different now, but you want to be strategic. So, you know, think about where the stresses are going to concentrate in this model. So if it's going to concentrate, you know, is it going to concentrate in the post or is it going to concentrate in the sign? Okay? And so based on where you see the higher stresses, you know, that's where you want more elements. And then for the areas that don't have a lot of stress, you can kind of portion up the elements in those regions. Okay. Yeah. Yeah. So you want to be a little bit strategic about it.
Smaller makes it longer. Change the size. So I got an error when I tried solving it. So I changed my method. I think that might. Yeah, I thought the limit was like 51,000. What? Now you're not. I think we're at 2. It's a good lesson, you know, it's not only, we still have.
All right, guys. So it's 6:20, and so it seems like you guys are making good progress. But I do want to give you guys a couple tips. Okay. All right. So And so I've gotten a lot of questions on the meshing. Specifically, for the last two activities, I asked you to do things like, explain kind of your thought process. And so, up to this point, we've had lectures on meshing, boundary conditions, and material properties. And so I want you guys to incorporate some of that information here. Okay? And so, for this activity, I'll be honest with you, I grade these for completeness. And so I'm not reading these things super carefully, but it's good to start thinking about this because, what's coming up next week is we're going to start working on the midterm project. And so you're going to need to have a good grasp of that theoretical information. So it's good to start thinking about this now so that on the project, you can explain those things. Because your projects, I am going to read very carefully. I am going to grade those a lot more harshly than your activities, okay? And so for instance, I'll give you an example, right? And so in our meshing lectures, we talked a lot about the relationship between element size and accuracy, right? And so the smaller your elements, the higher accuracy. And so it would be great, if we could just use really small elements everywhere and just maximize the accuracy, right? But in reality, we don't really have the time for that because if we use, such small elements that we end up with, 1 million elements here, you'd be waiting a really long time for your results. And a lot of times you don't have that time. Okay? And so, what I've been telling people is that, the reason this is an assembly where, you can assign a different mesh sizing to the sign versus the post is that it allows you to kind of strategically allocate where you want most of your elements to be. And so specifically, the one I want you guys to look at is the stress field, okay? And so if you've already run the simulation, you've probably seen that there's one part of your model, either the sign or the post, I won't spoil it for the ones that haven't done it yet, that has a lot more stress than the other one, okay? And so for that area of the model, which has a lot more stress, you're going to want to concentrate a lot more elements there just to make sure you estimate the stress a lot more accurately, okay? Another example of that is the shapes, okay? So these two geometries are very different shapes. So one is a literal rectangle and the other one is just a cylinder, okay? And so they're between the triangular elements and the rectangular elements, one of them is better at a certain type of geometry than the other. And so that's kind of the reasoning I want you guys to think about when you're choosing the size, when you're choosing the shapes. Think about the features of the geometry, think about what you're trying to get from the simulation, and think about what's going to be most appropriate for that. Okay, and so there's that part. So the other part I want to, so a lot of this activity I think is fairly straightforward. Okay, and so I want to talk about problems 5 and problem 6. Okay, so problem 5 is post design. And so for this one, after you kind of run your results and you had your mesh. And so I want you to change the geometry of the post to make it so that the results have less stress, basically. Okay. And so to do this, you're going to have to open up the part in Design Modeler. And so if you open up Workbench, okay, you go to Geometry here, you right click and you click on Edit Geometry in Design Modeler. You can change things like you can change the diameter of the post, you can change the width of the sign, you can change the size of the sign so you can make it smaller. Okay? And so I want you to make at least one change to the geometry that will result in a smaller amount of stress. Okay. And so I'll let you guys kind of play around with that and decide that. But that's what I mean by post design. Okay. In problem 6, what I want you to do is, and you can do this on the modified geometry, you can do it on the original one. It doesn't really matter to me. I want you guys to think of different loading scenarios. And so, I gave you some loading here where we're basically simulating the weight of the signpost, as well as a couple of wind forces. And so I want you guys to think of, what are some other typical forces that could be applied on a freeway signpost and then apply them into the model, okay? And so this goes back to our lectures on boundary conditions and thinking about, what's the physical situation that the signpost is going to be in and how can you model that with boundary conditions, okay? So I'll give you an example. And so, and because I'm saying this, you can't use this one, but imagine that you had a really fat pigeon that's sitting on the top of the signpost, okay? And so you can model that fat pigeon, let's say that it's just sitting on the very edge, okay? Okay, imagine it's a school of pigeons, okay? So it's a lot of pigeons sitting in a row, okay? And so what we can do then is we can apply a force here on that edge, a force that's vertically downwards to simulate all those fat pigeons sitting on that signpost, okay? So that's an example of a different load that you can add to this. And so I want you to think of 2 alternate scenarios and so 2 different types of loading conditions, and then and run the simulation for that and see how that affects your results. Okay. Yeah.
So I have two questions actually. So we're gonna do one at a time, so we're not adding our two at the same time.
Correct.
We're also adding these on top of all the stresses we added already, correct? It's
You-
not
you-
like we're getting rid of the others and then just doing one.
You can't get rid of them. And so actually the only one that I think has to be there is the fixed support and the weight. But you can get rid of the wind forces and add just the pigeon forces. Yeah. And so that's a good question. And so when I say two different loading scenarios, I mean one at a time. So don't just add two loads and just do it once. You know, add a load and then run the simulation and then maybe take that one away and add a different load and then run a different simulation. Right? And so when I say two different loading scenarios, I mean two different simulations, you know, that you have to run. That's different from the original. Okay. All right. Any other questions on this? All right. And so there is one last part to this activity, which is, you know, I want you guys to run a finite element analysis chair, which, you know, people have said this is the worst design chair they've ever seen. And so, you know, you can make fun of it if you want. And so just like the last activity, you know, this is just an additional one. You don't have to do a lot here. Just make sure that you kind of run some simulations on this chair. Just kind of follow the directions there as well. Okay. All right, so we have 15 minutes left, and so I'll continue making my rounds. And so if you have any other questions, just raise your hand. And then, you know, we'll go from there. But you can use it. Texas can work for our services. They can use if you make it small. Right? So that's good. So generally what you do. The same time, and that's the reason I don't want to. Because before you just. No matter how much you. The reason I. So yeah, so that's active. We should get back. Exactly. And in some sense, you know, you can't, because you have to actually try it out. But getting convergence is kind of the best. Yeah. Just make sure you kind of justify it. So I use Texas for this, but I made it small. You know, you can if you want, but you can use these, but by this point we want to modify this. Yeah. It shouldn't be like that. It should be around. Okay, so we try to understand. You want to make sure you're probably fit right.
3,900,000. Stepping down.
I mean, generally speaking, text and are the difficulty with text is that you can't always get them on. So text is basically a long process. Wow. Text would be more approval. It's kind of, well, for this one, it's so simple. Text is like in reality, that's kind of the tough thing, but for this one, like keep up with these factors. And generally, if you can get a text, that's usually better. Oh, okay. And so the limit. So, oh yeah, so the one thing I was figuring out, it's a slightly larger limit. So I think I was after this one, like maybe 100,000, but I have yeah, so when you add slides, so you automatically I will say that you don't really find it. You can get it. And so I wouldn't worry about that. Just know that it
Currently at a range of 8 to
Oh.
So usually, so I usually get like.
I think it's considered negative.
Recently.
I didn't even think.
Yeah, so I know something. I know you guys were like, so I know you guys were.
Why are you trying to fix me?
I went to my mom's house. Oh, I don't just wear like a cotton like blouse. I don't know.
That works.
Yeah, so most of the time, you know, for but actually, this one is so
Lisa has two parents. Person has two parents, both married, and the other one is a girl. And it's just like, no, I
So that's kind of another way. Actually, another way you can. So you can. We start here too. Yeah, so then you kind of have to realize all right, so we're just about out of time. So so thank you everyone for coming. You know, you have a little bit over a week for this. And I'll close it. All right, have a good weekend, everybody.
What was the minimum elements for the match?
There's no minimum, but there is a maximum. And so you should, most cases for this class, just because the maximum is so small, if you push it close towards the maximum, that's usually a good place you want to be. So the maximum is around 50,000 elements.
Okay, I got 13,000.
Okay, you can push that a little bit more. So
Okay. I tried to do that, it gives me errors.
okay,
So I can't get any lower. Try to get the elements size any lower.
okay, try to be a little bit, because you're changing the size, but you're changing the no by changing the size, right? And so try making the size changes a little bit more gradual.
Yeah. And also I'm getting, because of this new feature, I'm getting like a info. It's like not an error, but it's like they say, warning me that it may not calculate. So connections. I know yours doesn't say it, but mine. So like this one.
Change anything?
No, I just changed the name. That's it. I didn't touch anything. I just left it as it is. It just says info. It's not real. Okay. But that one, I don't know what they should do. Oh. That doesn't do it.
Okay.
It should be okay.
Okay. Yeah, and this morning just.
No, yeah, I actually I read that in that and the reason for it, and actually I looked online, they just say, because a lot of people were complaining that this isn't true hexagon.
All right.
So they added that feature to warn you, it's not a true hexagon.
Oh, okay. Well, a true hex mesh is really hard to do, unless you have a literal rectangle.
Yeah.
But I guess people want to see those things. So.
Yeah.
Okay.
I guess they got very Nancy boss.
But then the equivalent stress will show up on that. So what they're gonna check is the maximum, if that maximum is greater than. Because every material has a certain stress level that it can tolerate for it. And so if that stress is greater than. So every material has its own. The previous one, And so I think I mentioned somewhere in the activity.
Oh, you did as well?
Yes.
So for this one, you said something like 25,000.
Yes, exactly. So you're checking to see if the maximum stress is going to exceed that 25,000. Exactly.
Okay, so that's, you tell us usually, but like, otherwise.
Yeah, and so if you look at the material data sheet, it will be on. And I think for a lot of cases.
Yeah, and then you also asked us on the basis and you were like, oh, this material didn't take. Oh no, it does fail. Like adjust it such that it won't. I didn't understand how to do that. Yeah.
Okay.
I will.
The more force you apply to the more load.
So you were telling us, oh, we're talking about, you know, selling and don't use it, something like that.
Yeah.
Okay. Now.
Charles, you have an advising meeting tomorrow, right?
Yeah, I'll see you tomorrow.
Okay, I'll see you tomorrow.